Hello, everybody. I'm going to be giving notes a little bit differently today. I'm going to be going through this movie. I am with some HAL kids at an engineering competition today. So we need to learn how to balance redox reactions. So I have made this video for us to kind of go through the steps. We are going to be balancing redox reactions clearly, and actually the notes that we are going over today can be found in your redox packet starting on page 3. You are going to have to be able to know and be able to apply the 8 steps to balancing redox reactions. I really encourage you to take your notes on separate sheet of paper with so that you can really start to build that understanding about how we can balance redox. And it can seem a little bit confusing, but if you rely on the steps, it can make it a little bit easier. Now, you may remember when we first learned dimensional analysis, I taught the steps and I said that it really would not be appropriate for you to say, I do not understand dimensional analysis at all. But you could tell me which step you were getting lost on, and that would be an appropriate way to get help. Balancing redox is kind of the same idea. We're going to look at it as a process, 8 different steps. It is not acceptable for you to say, I do not understand how to balance redox at all, but you can say, you know what, I get stuck on step number 3 or step number 4, whichever step it is that you're getting lost on, so that we can really direct the help that you need in balancing these equations. We're going to go over 3 examples today, going through the steps. You're going to have 3 problems that are going to be homework, and then tomorrow's going to be a work day, and I'll be back tomorrow, so you'll be able to ask questions or get any help that you need. It is important that you realize that these redox reactions are occurring in an acidic aqueous environment. Remind yourself what it means to be aqueous. Now, I hope everyone thought in their head that aqueous means that we are in a water environment. And that's important because we're going to be using water to balance these, and sometimes it can get a little confusing about where the water's coming from. Well, it's actually coming from that aqueous environment. Now, this environment is also acidic. So remind yourself what it means to be acidic. And again, I hope that what came to mind is the H plus ions, because we'll also be using H plus ions to balance these equations. And again, it can be confusing if you don't realize where they're coming from, and they're actually coming from that aqueous environment. Now we're going to go through all 8 steps and take time to write these down. Hopefully my wait time is long enough so you have time to write these down. We'll then go, as we're going through the 3 examples, we'll look at each of the steps in order once again. So, steps to balancing a redox reaction. The first thing you need to do is split the reaction into half reactions, and that would be a reduction and an oxidation. Just as a reminder, reduction means that you are gaining electrons, and oxidation means that you are losing electrons. If you remember what we talked about last time, we talked about the method of assigning oxidation states. So what we really do in our redox equation is we assign oxidation states to each of the elements, and by examining those oxidation states, we can see what was oxidized and what was reduced. Now that oxidation is going to show an increase in their oxidation state, so they will become more positive or less negative, depending on how you want to look at it. And then if you are reduced, your oxidation state is going down, so you're becoming less positive or more negative. So we use those oxidation states in order to split the reaction into half reactions. The second step is to balance all non-hydrogen and non-oxygen atoms by adding coefficients. This really is no different than what we have been doing up to this point when we balance equations. We want the same number and type of atoms on both sides, and to accomplish that, we add coefficients in front of each of the species that we need to change the number of atoms that are present. The only thing that we're changing here is that we are only going to do this to non-hydrogen, non-oxygen atoms. So we're going to save hydrogen and oxygen to balance in a different way using water or H+, which we'll talk about here shortly. So we only use coefficients in front of our species to balance non-hydrogen, non-oxygen atoms. We're actually going to balance the oxygen by adding water. Now, again, this water is not coming out of thin air. It's coming from the aqueous solution where this redox reaction is occurring. And because it's an aqueous solution, we actually have water that is available to us to use in the balancing of our equations. So if I need 3 oxygen for whatever reason on one side of the equation, each water molecule would provide me with 1 oxygen, so I would have to add 3 water molecules to the side that I need 3 additional oxygen to, and that is how we are going to be balancing our oxygen, by using the water from the aqueous solution. Well, we are then going to balance our hydrogen by adding H+. Now again, these H+ ions are not coming out of thin air. They're coming from that acidic aqueous solution where we have plenty of H+'s to use in the balancing of our hydrogen. Now every time that we add water to balance our oxygen, that's going to introduce hydrogen to our equation, and we have to have a way to balance that. And again, the way that we balance that is by using H+. So we're going to use H+ to balance our hydrogen. The fifth step, we're going to balance the charge with electrons. So we're going to really examine the charge on all of our species on the reactant side, and we're going to examine the charges on all of our species on the product side. And if the charge is not the same on both sides, we are going to add electrons to make the charge the same. Now, by adding electrons, think to yourself, what is that going to do to the overall charge on the side that you add electrons to? Hopefully you thought about electrons being negative, which means whichever side we put electrons on, we're going to cause it to be less positive. So we can't take a side that's more positive and add electrons. We're going to add electrons to make it less positive. But the charge on both sides needs to be the same. And we actually do this process to both of the half reactions. So we look at the oxidation half reaction, make sure the charges are the same on both sides. If they're not, we're going to add some electrons. And we'll do the same thing with the reduction half reaction. Now clearly, because oxidation and reduction involve a transfer of electrons, we are always going to have to add electrons to one side or the other in each of these equations in order to have the charge be the same. If that's not the case, then you probably made a mistake somewhere. So we're going to balance the charge on both sides of both half reactions by adding electrons. The sixth step, we're going to multiply our half reactions by some integer or whole number to make the electrons lost equal the electrons gained. If you remember, up to this point, a balanced equation was simply having the same number and type of atoms on both sides. Well, the redox reaction introduces this idea of electron transfer. Well, in order for us to be balanced now, we also have to make sure that the electrons that are transferred are balanced as well. So whatever number of electrons we lost has to equal the electrons that we gained. if we lost 2 electrons but we gained 4 electrons, we would have to go back to that oxidation half reaction and multiply all of the coefficients by 2 so that the 2 electrons that we lost become 4 electrons to match the 4 electrons that we gained. Again, we're going to see examples of this so you can see what this looks like in the process of balancing these redox reactions. Now, these redox reactions, as you're balancing them, can get pretty messy. So you want to be very meticulous and organized in your work so that if you do make a mistake, it's easy to go back and look at your work to figure out where that mistake happened. And again, if you feel like you're in an infinite loop, completely start over. It's really easy to make a simple mistake in these and not be able to balance them. So be meticulous, follow the steps, and it's not as horrible as it may seem with having 8 steps to go through. The 7th step, we're going to add the half reactions and cancel the substances on both sides. So we're going to have 2 half reactions. We're going to add the reactants together. We're going to add the products together to get an overall equation. And because we're using water and hydrogen to balance our oxygen and our hydrogen, those H plus ions, there is a good chance that you could have water on both sides, or you could have hydrogen, H plus, on both sides, and you would cancel out. If they're on opposite sides, you would cancel them out. So if one of my equations had 8 H plus ions as a product, but the other one had 4 H plus ions as a reactant, those 4 H plus ions as a reactant would cancel out 4 of the 8 H plus ions on the product side. And again, we'll see this in work, how it works. But if they're on both sides, they would cancel out. Think math. It's really just kind of a math process. And then, of course, the last thing that we want to do is we want to check that the number and type of atoms are on both sides are the same, and that the charge is the same on both sides. And if they are, then we balanced it correctly. If they are not, then we made a mistake somewhere and we need to go back and check our work. It really is an important step. You will always know once you have added your half reactions together, if you go back and make sure that the number of atoms and the type of atoms on both sides are the same, and that the overall charge is the same on both sides. If that is the case, it's balanced. You did it correctly. If that is not the case, then you are not balanced, and we have to go figure out what we did wrong. All right, so let's look at the first example. I believe this is the very first example after the steps. And this is a pretty simple redox reaction. In fact, I think everyone in here could balance it without going through the steps. But it's nice to kind of start with something that's simple in order to look at all of the steps. Now, if you look at the top of the slide, each slide that we go to will have the step at the top that we're working through. So this is step 1. We need to split the reaction into half reactions, which will be a redox, a reduction, and an oxidation. Now, think to yourself, how are we going to recognize what was oxidized and what was reduced? Hopefully what you were thinking was assigning oxidation states. So we have zinc in its solid form, which is its elemental form, so its oxidation state is going to be 0. H plus is an ion, and hydrogen is always a +1, so unless it's in its elemental state. But as an ion, hydrogen is going to be a +1. Zinc as an ion is a 2+, so its oxidation state is a +2. And then we have H2 gas, which hopefully you recognize as elemental hydrogen, and that would have an oxidation state of 0. So now that we have assigned all the oxidation states, we can examine what has happened to those oxidation states. So zinc started at a 0 and became a 2+. That's an increase in oxidation state. So that would be our oxidation half reaction. The fact that zinc that was 0 became a 2 plus. That happens when you lose electrons. That is our oxidation half reaction. If zinc was oxidized, then hydrogen had to be reduced. Hydrogen was at a +1 oxidation state. It goes down to 0. That is a reduction in its oxidation state, which means that it had to gain electrons. And hydrogen is our reduction half reaction. That is step 1. All right. Step 2, we're going to balance all non-hydrogen, non-oxygen atoms by adding coefficients. Well, if we look here, the only non-hydrogen, non-oxygen that we have is zinc. Here I have 1 zinc. Here I have 1 zinc. Since the zinc is already balanced, I do not need to add any coefficients. So I am now finished with step 2. Step 3, we're going to balance oxygen by adding water. And again, that water comes from our aqueous solution. Well, we have no oxygen, which means we do not need to do step 3 either. And again, I said this was a really simple redox, so we're starting simple. We're going to get more complicated as we go on. But we did not need to do step 2 because our zinc were already balanced, and we don't need to do step 3 because we do not have any oxygen. That brings us to step 4. Step 4, we need to balance hydrogen by adding an H plus ion. Our H plus ions, if we look down here, we have 1 H plus. Here we have 2 hydrogen. So we need to add a coefficient of 2 in order to get 2 H pluses. Now this is kind of unique that we already have an H plus. You will see as we go on that sometimes you don't have H pluses already in your equation, which means that you would have to physically add H plus to your equation. But here we can just add a coefficient and now convince yourself that we have 2 hydrogen on both sides. All right, step 5, we're going to balance the charge or oxidation number with electrons. So looking at this oxidation half reaction, on the reactant side, zinc is neutral because it's in its solid elemental state. On this side, zinc has a 2 plus charge. So we have a neutral charge on our reactants, a 2 plus charge on our product side. We need to have the same charge on both sides by adding electrons. So the only thing I can do, I cannot make this more positive. All I can do is bring the 2 plus down to neutral. To do that, it's going to require 2 electrons. When I have a 2 plus and I add 2 negative, I'm now neutral, which is the same as the reactant side. We do the same thing in our reduction half reaction. So this side is neutral because hydrogen is in its elemental state. This side is a 2 plus, and it's a 2 plus because I have 2 of these H plus ions. Again, I need to add electrons so that I have the same charge on both sides. The only thing I can do is bring this 2 plus down to neutral by adding 2 electrons, now making that neutral, and now I am neutral on both sides. So the number of electrons, as we'll see in the next step, we're now going to compare the electrons that we lost to the electrons that we gained. So step 6, we're going to multiply by some integer to make electrons lost equal electrons gained. Well, zinc had to lose 2 electrons to become a 2 plus, and hydrogen 2H plus ions have to gain 2 electrons to become neutral. Therefore, because zinc lost 2 electrons and hydrogen gains 2 electrons, they are already balanced. So we do not need to multiply either of these half reactions. They are we already have the same number of electrons on both sides. So then the last thing we're going to do, well, the next to the last thing we're going to do is add our half reactions together and cancel out any substances on both sides. Now, every time that you do step 7, your electrons should cancel out. The 2 electrons on the reactant side cancel out the 2 electrons on the product side. And so we should never have any electrons in our equation that we add together. So when we put this all together, we have zinc right here. We have 2H plus, which is right here. We have those are our reactants. They react to form zinc 2 plus, which is right there, and H2, which is right there. So that is our that is the process of adding up our half reactions. Now, of course, the last step is to check to make sure your atoms and charge balance on both sides. So we start counting atoms. Here I have 1 zinc. Here I also have 1 zinc. Here I have 2 hydrogen. On the product side, I also have 2 hydrogen. So all of my atoms balance. The next thing I'm going to check is my charges. So I have zinc, which is neutral, added to 2 H pluses, which gives me a 2 plus, which gives me an overall 2 plus on the reactant side. On the product side, I have zinc, which is a 2 plus hydrogen, which is neutral, which is also equal to a 2 plus. So as you can see, our charges are the same on both sides, which means we are balanced. So this was a very simple example of a redox reaction, but I think it's nice to kind of go through something simple with those 8 steps. So now let's complicate things just a little bit, nothing horrible, but we're going to have to be using water and hydrogen in the next example. So take some time to write down this example. We're going to take iodide and react that with nitrite to form iodine and nitrogen monoxide. First thing we have to do, split reaction into half reactions. So, whisper to your neighbor how we are going to do that. Hopefully you guys whispered that you need to assign oxidation states. So iodide with a -1 charge would have a -1 oxidation state. In nitrite, we always know that oxygen is a -2. That gives us a -4, which means our nitrogen must be a +3, so that when we add these up, we get a -1. Iodine in its elemental state is 0. And then again, we know the -2, which means this nitrogen must be a +2. All right, examine the oxidation states and whisper to your neighbor again which element was oxidized. Which element was oxidized and how do you know? Hopefully you recognize that iodine went from a -1 up to 0, which is an oxidation. So our oxidation half reaction becomes iodide reacting to form iodine. And now whisper to your neighbor which element was reduced. Again, if an element is oxidized, something else has to be reduced, and nitrogen went from a +3 down to a +2, which is a reduction. So our reduction half reaction becomes NO2-, forming NO. So there is step 1. Step 2, balance all non-hydrogen, non-oxygen atoms by adding coefficients. Right, in our oxidation half reaction, do we need a coefficient to balance our iodine? The answer is yes. We need a 2 in front of the iodide to get 2 atoms of iodine on both sides. In our reduction half reaction, do we need any coefficients to balance our nitrogen? Nope, there's 1 atom on both sides, so we do not need a coefficient, and we are not going to balance oxygen at this time because that's what we are going to do in step 3. So here is step 3. We're going to balance oxygen by adding water. Again, coming from that aqueous environment. In our oxidation half reaction, we don't have any oxygen, so this is not an issue. In our reduction half reaction, we have 2 oxygen in our nitrite, but only 1 oxygen in our nitrogen monoxide. Therefore, we have to add 1 water molecule to the product side so that we now have 2 oxygen on both sides of the equation. So this water came from that aqueous solution. We need that water in order to balance our oxygen. All right, step 4. We're going to balance hydrogen by adding H+. Now again, we don't have any hydrogen in our oxidation half reaction, but by using water to balance our oxygen, that changes our hydrogen. So on the reactant side, we don't have any hydrogen, but on the product side, we have 2 hydrogen. Now, in order to get 2 hydrogen on the reactant side, we have to add 2 H pluses. Again, those are coming from the acidic environment, and that now balances our hydrogen. So at this point, all of our atoms should be balanced. So the next thing that we have to look at are the charges. So in step 5, and as you can see, we now have 2 hydrogen on the side. At step 5, we're going to balance the charge with electrons. So if we look at our oxidation half reaction, on the reactant side, we have a total of a 2- charge because we have 2 of these iodides. But we are neutral on our product side. Whisper to your neighbor which side we need to add electrons to and how many we need to add to have the same charge on both sides. All right, did you say that you needed to add 2 electrons to the product side? That gives us a 2- now on this side, which matches the charge on our reactant side. Let's try the reduction half reaction. Here I have a 2 plus minus 1. So 2 plus minus 1 is a 1 plus on the reactant side. On the product side, we have a neutral and a neutral, which means that the overall charge is neutral. Again, whisper to your neighbor which side we need to add electrons to and how many in order to have the same charge on both sides. Did you say 1 electron on the reactant side? By adding 1 electron to the 1 plus charge we already had, that brings it down to neutral so that we are now the same on both sides. Okay, our atoms are balanced. The next question is, are our electrons balanced? So we need to multiply by some integer to make electrons lost equal electrons gained. Now here we have lost 2 electrons, but we have gained only 1, which means we are not balanced. We've lost 2, but we've gained only 1. So we must multiply this reduction half reaction by 2. So that'll change all of the coefficients. So 1 electron will become 2 electron. 2 hydrogen will become 4 hydrogen. We will now have 2 NO2 minus and 2 NO and 2 H2O. And what does that do for us? We now have gained and lost the same number of electrons, which makes us balanced. All right, we have now lost and gained 2 electrons, and that's what we're trying to do. So we now need to add our half equations together and cancel substances on both sides. Okay? Again, whisper to your neighbor what should always cancel out when balancing a redox reaction. Did you say that the electrons should cancel out? So we have our 2 electrons on the reactant side are canceled by the 2 electrons on the product side. None of our other species are repeated on either side, which means nothing else cancels out. So our net reaction, when we add these together, we have 2 iodide, 4H plus, 2 NO2 minus, I2, NO, and 2 H2O. So we remove anything that is on, has the same amount on both sides. All right, the last thing that we need to do is we need to check our work. So let's start counting our atoms. 2 iodine, 2 iodine, 4 hydrogen, 4 hydrogen, 2 nitrogen, 2 nitrogen, 4 oxygen, and here we have 2 oxygen plus 2 oxygen, which gives us 4 oxygen. So all of our atoms are balanced. The last thing we have to check is the charge. So we have, on this side, we have 2 minus, which is right there, 2 minus, 4 plus, and 2 minus. So 2 minus plus 4 plus 2 minus is neutral. And then on this side, we have neutral, neutral, neutral. And now we are the same on both sides. So we are balanced. All right. We're going to make this one a little more complicated than the last one. So write this next problem in your notes. And I think I skipped 1 or 2, so this is in your notes, but I'm not 100% sure which number it is. But again, we need to split the reaction into half reactions. So copy this down. CrO4 minus plus S2 minus goes to form Cr3 plus SO4 2 minus. I'm going to have you go ahead and assign oxidation states and split it up into your oxidation half reaction and your reduction half reaction. And here comes some fun music. All right, let's see how you did. Here are your oxidation states. So we know oxygen is a -2, which makes chromium a +7 in that chromate ion. Sulfur is a -2 because of its charge being 2-. Chromium right here is a +3 because its charge is a 3+. And then we know the oxygen and sulfur. So sulfur was oxidized, went from a -2 to a +6. So our oxidation half reaction becomes S2 minus, forming SO4 2 minus, and chromium was reduced and went from a +7 down to a +3. So our reduction half reaction is CrO4 minus going to form Cr3 plus. All right, step 2. Balance all non-hydrogen, non-oxygen. All right, go. Now, you probably didn't need much time here because it's already balanced. We have one sulfur, one chromium, and so our non-hydrogen, non-oxygen are already balanced. The next thing we need to balance are our oxygen by adding water. So again, here comes the Jeopardy music. Go ahead and balance your oxygen by adding the number of water that you need on the appropriate side to have the same number of oxygen on both sides. All right, so did you add 4 water to the reactant side in order to get 4 oxygen? And did you add 4 water to the product side in order to get 4 oxygen? Now our oxygens are balanced, but we introduced hydrogen. Whisper to your neighbor what we use to balance our hydrogen. Did you remind your neighbor that you need to use H+? All right, so again, balance your hydrogen on both sides by adding H+. All right, so by adding 4 water, we introduced 8 hydrogen, so you're going to need 8 H pluses on the opposite side in both half reactions. Give your neighbor a fist pump if you both got that correct. Okay, now we need to look at the charges on both sides. So you want to balance the charge on both sides, and I'm going to tell you this one's a little bit tricky, so figure out the charges on both sides of both half reactions and add electrons to the appropriate side to make it the same. Here we go. All right, this one was a little bit tricky. If you look here, you're going to need 8 electrons on the product side of the oxidation half reaction in order to get the same charge. And let's look at the charges. Well, I guess first we'll look at, we need 4 electrons on the reduction half reaction on the reactant side in order to get the same charge. Now let's look at the charges. So here we have neutral plus a 2 minus, which gives us a 2 minus charge. Here we have a 2 minus and an 8 plus, which means we need an 8 minus in order to bring it back down to a 2 minus to match this side. Down in the reduction half reaction, we have a 4 minus plus 8 minus 1. That gives us an overall 3 plus. And on this side, we have a 3 plus plus neutral, which is a 3 plus. All right. Next step, we need to multiply so that the electrons lost equal the electrons gained. Let me get your music again, and you can try to do this as well. All right. Hopefully you realize that we lost 8, but we gained 4. So we must multiply the reduction half reaction by 2. So 4 electrons become 8. 8 H pluses become 16. We have 2 chromate, 2 chromium, and 8 water. All right, now you need to add your half reactions together, canceling substances on both sides. Again, be careful. This one's a little more complicated. All right, let's go ahead and try it. All right, so your electrons should always cancel out. And then if you notice, we have hydrogen on both sides. Well, these 8 hydrogen will cancel 8 of those 16 hydrogen, leaving you with 8 hydrogen on the reactant side of your reduction half reaction. And then if you notice, we have water on both sides. So these 4 water will cancel out 4 of those 8 water, leaving you with an equation of 8H plus 2CrO4 minus S2 minus 2Cr3 plus 4H2O and then just SO4 2 minus. So hopefully you can see how you can cancel out some, if not all, of your species that repeat. Right? Last thing we need to do is check that our atoms balance and the charge balance. So we have 8 hydrogen on both sides, 2 chromium on both sides, 8 oxygen, and here we have 4 oxygen in our water and 4 oxygen in our sulfate, giving us 8 oxygen. We have a single sulfur on both sides, so all of our atoms balance. The last thing we need to check are the charges. So we have an 8 plus a 2 minus, plus a 2 minus, which gives us a 4 plus. And on this side, we have a 6 plus water is neutral, plus a 2 minus with our sulfate, which also gives us a 4 plus. So we are balanced. Hopefully you're getting comfortable with these steps. Your homework are numbers 3, 5, and 6 from the notes pages in your packet. And as always, I'll have these answers on the board tomorrow. And then tomorrow's a work day, so if you need some help, you can certainly ask some questions tomorrow as well. We will have a 100-point quiz on Thursday, so make sure you are ready for that. Hopefully this worked out okay, and I will see you tomorrow.